So I just posted the, excuse me, on the board anyway. Here's the recommended homework for the first 5 sections in Chapter 3. Basically, the next test is on Chapter 3, give or take. Now, there is a little bit of material that I've omitted. I would say the main thing that I've omitted, which you would, likely find, for example, if you're in another section of pre-calculus, like the other section will most likely cover synthetic division. I won't cover synthetic division. I don't have anything to say about synthetic division, except to say that I'm not covering it. Okay. We'll do long division in here. So I have tried to remove any problems which I think assume the use of synthetic division. All right. But here you go. This is the recommended homework to start with. I mean, there's also sections, let's see here, 3.6 and 3.7. And so I'll pick those problems out, and I'll type this up and put it in an announcement as well. So you don't have to copy all these numbers right down right now. But just in case somebody's waiting to get started on the recommended homework, here's what I recommend. All right. And mission 4, I will work on posting sometime pretty soon. So hopefully that will actually happen. Any questions? All right, so I'm going to try to get straight into it then. So I guess the first question I have for you is, do you guys know how to factor? Have we talked about factoring in here yet already? I mean, I think I spend about a week and a half on factoring in the intermediate algebra class, right? So if you're rusty on that, you can go look at those videos if you want. I do factoring after factoring after factoring at a probably much slower rate than I will in here, But hopefully we know factoring from, from that class. So are you guys good on factoring? Should we review? Good. So I'll just say we're going to talk today basically about graphs of polynomials. And so what I'm just saying to start with is that if you're not good on factoring, you'll need to review that, because that's going to be a major ingredient for what we do. So first of all, let me give us a definition. What is a polynomial? Right? So f of x equals to, say, an x to the n plus plus a2x squared plus a1x plus a sub 0 is a polynomial, right, of degree n, provided what? A0, A1, an are constants, and we need that a sub n is not equal to 0, right? What are the name of these constants? Do they have a name? What are the numbers that multiply the powers in the polynomial? What do we call those things? What's the name of these constants? You guys aren't going to name names? All right, fine. These are called coefficients. Right? And so essentially, if you tell me the coefficients for a polynomial, that's kind of its DNA, right? Once you give me coefficients, I can write down the polynomial, right? So there's like a one-to-one interchange between those numbers and the polynomials. Okay, so the first thing we can do, of course, is basic graphing. We've already talked about that, right? So the basic graphing, the first line of defense essentially is to look at y equals to x to the n and transform, right, using our transformation tricks, right? Up, down, left, right. Etc. Right? So that's the first thing we could try. That could have been it. Too much. So for example, if I have y equals to x squared plus 1, I ought to be able to graph that polynomial function by doing what? I think in my mind, y equals x squared. It's a parabola that opens up, right? So this, I just take that, and it opens up from the origin, and I shift it up 1. So this has graph like that, you know? And that, there you go. That is my process for graphing x squared plus 1. I just think through the transformation in my head and write it down, you know? Another example, if I had y equal to x minus 1 cubed, right? Well, what is that? That's the cubic graph, right? And we shift 1 to the right if we subtract 1. So that's basically going to go through 1 and look something like this. I can't graph. Come on. Well, I tried. I'll work on being better. It's so sad. I have to erase it. It's just too horrible. Try this again. Now my graph is not quite right in the sense that this point is what and this point is what. Like what's the point on the x-axis called? It's called the x-intercept, right? What's the point on the y-axis called? Y-intercept. So these are basic. One of the two. There's a lot of things that we can look for to give structure to our graphs, right? But one of the two basic ingredients we can look for is x-intercept and y-intercept. So how do we find those? X-intercept is what? Is where what? Where y equals to 0. And the y-intercept is what? Where x equals to 0. So for this graph, what's the x, for the example right above, let me number these, example 1, example 2. For example 2, what's the x-intercept, what's the y-intercept? Now how did you said -1 for the y-intercept, how did you know that? I mean, I'm not disagreeing, you're right, but why is that? Why is, if this is f of x, how did you get the y-intercept? What did you do?
It's when it transfers.
Yeah?
It just crosses the graph right there.
Yeah, it crosses right there, but I mean, my question is, how do you know that that's -1?
Oh, because the -1, whenever you're trying to find the y-intercept, you'll just use that, or you'll minus it, x minus 1 equals 1, or yeah, x minus 1 equals 1 on both sides. But when you're doing the opposite, when you're trying to find the x-intercept, you just use that.
Right, when we do the x-intercept, we look at the factoring, we go, it's the opposite for the factoring, right? So you're saying that this is 1, because that's a -1, that makes this, the x-intercept, a 1? Right. I totally agree with that. And you're not wrong that the y-intercept is -1, but I want us to understand where that's coming from, and it's not too complicated. To find the y-intercept for a graph, we just have to take the function and evaluate at 0. F of 0, that's where the graph is when x equals to 0. We plug 0 into the function. That tells us what the value of the function is at 0. That's the y-intercept. So what happens when you plug 0 into this? You get what? Yeah, I get -1 because I get 0 minus 1 cubed, which is -1 cubed, which is just -1. All right? So if we want to find a y-intercept for anything we're graphing, any polynomial we're graphing, it's pretty simple. We just plug in 0 into the formula and see what happens. What's going to happen? Yeah, for the x-intercept, we got to set the polynomial equal to 0, and that's basically solving the equation x minus 1 cubed equal to 0, which happens to only have the solution here of 1. But notice that, like, for this arbitrary polynomial, what's the y-intercept going to be? If we look at y equals f of x for this guy. Yeah, what's the y-intercept of this one? Right, yeah. F of 0, which you said is a0. This is the so-called constant coefficient. Right? And so the constant coefficient in a polynomial is the y-intercept, right? So this is something we should know because it helps us graph, confidently. All right, so basic graphing, we can take, one of our standard monomials, either x squared or in this case x cubed, to move it around, flip it upside down, flip it over. We can do stuff like that. That's one of the basic graphing ideas, right? But that's not going to help you graph something much more complicated, right? So if you want to graph something like example 3, right? If we were going to say y equals f of x equals to, let's say, x plus 2 times x minus 3, right? If we were going to graph that, how would we do it? What's the, graph this? How would we graph that? We'll try to at least be careful about the x and y intercepts to start with here, right? You guys tell me what are the x intercepts? What are the y intercepts for this one?
The x-intercept is -2.
Negative, right? -2 and +3, right? Nope. F of 0, right? What's f of 0 equal to here? Yeah, 2 times -3, right? Which is -6. So the y-intercept is -6, and the x-intercepts are like, yeah, -2, let's say here, and 3, I'll say, over here, I'll try to be somewhat, I'll give it a go to try to be, let's see here, it should be a little bit lower than that, somewhere down here. So -6, -2, 3. And, I'm not quite happy with that. I mean, I'm not, that's not wrong, right? But I still don't quite know what the parabola looks like, right? How can we improve on that? I think I told you guys about this already, right? Find the what? Well, how about can we find the vertex of the parabola? That would improve our graph, wouldn't it? How would we find the vertex of the parabola? What's that? You don't know how to find it with 2 x's. Okay. Right. So what we're going to do is multiply it out. That gives us x squared minus x, right? Minus 6. That's the polynomial in quote-unquote standard form. Then we'll complete the square on this, right? So this is equal to x minus 1/2 quantity squared minus 1/4 minus 6. Let me clean that up a little bit. So we got y equals to x minus 1/2 squared. How many fourths is a 6?
Is it 6?
Yeah, 6 is how many fourths? You got $6. How many quarters you got? yeah, 24 quarters, right? This is 24 quarters, so we got like -1, -24, -25 fourths is what I'm trying to get to here. And so like once I see that, I can tell you from this by inspection what the vertex is, right? That tells me what the vertex is. Where's the vertex? I'll do the easy part. 1/2. I mean, I think they're equal easiness actually, but what's the other? The y coordinate. When we put in x equal to 1/2, this goes to 0, right? Think about it. If you plug in 1/2 into this, that zeroes out, and it just leaves you this number. That's where the vertex is. When we plug in the x coordinate of the vertex, minus 25 fourths is the next thing here. Now my question to you is, where is this vertex? And maybe it helps to put this in like decimal form, right? That's 0.5. And what is that? That's minus 6.25, right? By the way, when you're thinking about making graphs, it wouldn't be wrong to go directly to like switch this over to decimal earlier on, right? Because you guys think in decimals, right? When you're actually thinking about plotting a point. I do anyway. I mean, once I see when I see 0.5 minus 6.25, I kind of know where that is on the plot, right? Where is it? It's pretty close to there, isn't it? The y-intercept is actually really, really close. That's the vertex. It's about right there-ish. So it's a little bit below the y-intercept, right? It goes a little bit lower. That's, in fact, if we think of this as a quadratic model, the minimum value is what? The minimum value here is minus 6.25. And that global minimum is attained at 1/2. Now, like the specificity and the care with which I'm graphing this parabola, this we cannot do for like higher order polynomials. You know, like you had a problem on the test where I asked you to graph, you know, the polynomial, and you had it was already factored, right? You're supposed to figure out the number of local maxes and local mins for that problem, remember? Like, where are the local maxes and mins? That I didn't ask you because you can't figure that out without calculus, all right? So this kind of like super careful picture of what the quadratic looks like, this is special. Like, we can only do this for the quadratic. Y equals to a quadratic, all right? We know a lot of stuff about quadratics. The higher order polynomials, though, mostly we're going to work with the X-intercepts and just try to get like a kind of a good sketch of it. All right, so let's go on here. All right, so the main theorem we have is the following theorem. And this is called the Factor Theorem. Right, so here's what it is. If f of x is a polynomial, all right, and f of c is equal to 0, then x minus c is a factor of f of x. So this is super useful because it gives us a link between evaluating the function, right, and finding that factor. And of course, we use that. I mean, that's kind of in the water here already, right? Like, what can you say about this previous example 3, right? You can see this theorem in action in example 3. What is f of minus 2? F of minus 2 is equal to 0, right? And x plus 2 is factor of f of x, right? And f of 3, right, is equal to 0. And indeed, x minus 3 is a factor of f of x. That's the factor theorem. So let's look at an example that's a little bit trickier, all right? So we find one of the ones from your recommended homework here. See if we can put this example theorem into play here. So this is from your section 3.2. It's like factor the polynomial and use the factored form to find the zeros. Now I'm going to ignore the instructions here pretty much. I'm going to use the factor theorem to try to help us out. Let's look at this. This example is from number 37. I'm not following the instructions to number 37, mind you. I'm just using the formula there. So anyway, what's given there is p of x. And the book tends to use p for polynomial. I use f for function, but don't make really no difference. Just p versus f. It's really not a just labeling x cubed plus x squared minus x minus 1. So I think, we might be able to figure out how to factor this without the factor theorem, right? Maybe. But the first thing I try in this course, and indeed any course where I'm working problems from a book, is I try to just plug in 1 into the polynomial and see if 1 is like x minus 1 is a factor. Sometimes that works. What happens when you try p of 1 here? What's p of 1 equal to? It's 0 because it's what? It's 1 plus 1 minus 1 minus 1. So yeah, so 0. And so what does that tell us? That tells us that we can factor out x minus 1. Now, how do you factor out x minus 1? There are various strategies. One strategy is factoring by grouping. If you can see that, that's pretty fast. Another strategy is long division. Which way do you guys going to... I'll let you choose, Heaven. You choose. Long division or factoring by grouping? I'm giving you control. I'm just ruling out the one option that... and so you're going to say, let's end class right now. But I'm forbidding that option. Before... Grouping? All right. All right. Heaven's like, you're starting to understand me. Let's hear now. The x, man. I see an x plus 1 factoring out, but the x minus 1 doesn't. Man, the x minus 1 is not popping out at me. I don't, do you guys see it? Yeah. You see x squared minus 1? Yeah. Like I personally don't see it. I mean, what I'm trying to say is I can say this is, x squared times x plus 1 minus x plus 1. Like that factoring by grouping pops out at me. So I can factor out x plus 1, right? What does that mean? If I can do that, tell me what else must be true about this polynomial. So x squared minus 1, how's that factor? X plus 1 times x minus 1, right? Difference of squares. So it's kind of funny in the sense that what I did in blue didn't help us directly. At least it doesn't help me. I can't. The factoring by grouping for x minus 1 just doesn't pop out at me. But there it is. I mean, this is the complete factorization of p of x. We found it anyway. Just not in the way I had hoped. So, all right, so what I'm trying to say here, guys, factoring by grouping is a little dicey, right? If you don't see it, you don't see it, right? Agree?
Correct.
So what about long division? Is long division dicey? Or is it something we can do methodically and every time? We can do it, right? Let's try long division here. What's long division look like here? We got ourselves x cubed plus x squared minus x minus 1. I want to divide x minus 1 into that. So I start out, I put x squared. That gives me x cubed minus x squared. I subtract. That gives me 2x squared minus x minus 1. How can I get 2x squared from x minus 1? I need to multiply by 2x, right? So I do plus 2x. So 2x times x minus 1 gives me 2x squared minus 2x. And then I have to subtract again, right? The 2x squareds cancel. What's minus x minus a minus 2x? That means sorry, I'm getting too low here. It means I add 2. What I'm trying to say is I've got x minus 1, right? Hey, that's nice. How many times do I need to multiply x minus 1 to get x minus 1? One time, right. So plus 1. And then you see we get 0. Which is what should happen if it's a factor, right? If it's a factor, there should be no remainder. And so what this calculation shows you is that, x cubed plus x squared minus x minus 1 divided by x minus 1 is equal to x squared plus 2x plus 1. You see how does that help us? We multiply x minus 1 to the other side, and it gives us what? right? So long division allows us to divide out a factor in this way. This is not an obvious idea. Like, I'm sharing with you a pretty significant trick, you know? And how about x squared plus 2x plus 1? How does that, can we break that down further? Continuing, right? So what we have is we've got f of x equals to x minus 1 times x squared plus 2x plus 1. But notice that factors, right? That's x minus 1 times x plus 1 squared. And I seem to have changed from p to f. I shouldn't do that. This is p of x, right? Sorry about that. I mean, you can call it p or you can call it f, but you got to stick with the same letter the whole time, you know? And so that's completely factored. Can we graph now? Yeah, we have all we need to write down x-intercepts and y-intercepts, right? So to graph y equals to p of x, we note p of 0 is what? So when you do p of 0, go back to the original formula. Plug 0 into the easy formula, the one that was given at the start. When we plug it in here, we get what? Minus 1, right? So minus 1 is the y-intercept. And how about x-intercepts where? At 1, yeah. And also minus 1. And, you know, there's another result that we need to keep in mind, right? So here's like a little theorem, if you like. If x minus r to a odd power factors p of x, then graph crosses x-axis at x equals to r. If x minus r to an even power factors p of x, then the graph bounces off x-axis at x equals to r. So that's a guideline. As we're thinking about these graphing, like, yes, we've got x-intercepts, but what's the nature of the x-intercept? Is it a crossing or is it a bounce, right? And so notice that here, x minus 1 has a power 1 up here that's odd. So this one, it crosses. And x equals minus 1, that's from this guy, right? Bounces, because that even power. So we have everything we need to graph, then let's graph. Here's minus 1, here's 1. Y-intercept, so y-intercept is minus 1, and it crosses at 1, and it bounces at minus 1. So I think I can pretty well draw the graph from that information. Bounces here, bounce, and then crosses back up here, like that. There you go. That's y equals to x cubed plus x squared minus x minus 1. Now, you guys have a significant advantage in the sense that you can double check your answer with a graphing calculator, right? You can plug the formula in and see, was I right? Did it actually look like that? Or did it not, you know? So. Let me ask you a question. So, can you tell me what I want you guys to do? I want you to be creative here for a second. I want you to come up with an example for me. So here's the question. Can you find P of x of least degree for which the y-intercept is 10 and it has x-intercepts of, let's say, -4, 2, and 3, where it crosses through -4 and 2, but bounces off 3. So can you guys tell me what's the formula? First of all, ignore the y-intercept to start with. All right, we're going to ignore that. How can we get it to cross at -4? What do we need as a factor? We're going to use the factor theorem to build this example. What's that? Yeah, odd power. And so we want it to be least, so we'll go with first power is enough, you know. So get us started, we want x plus 4. Right? That'll be part of it. And then what else do we want? X minus 2. Yep. And then what about 3? We want x minus 3, right? And I heard a square, exactly, to make it bounce. And now we're good. Now here's my question to you. If I put 17 here, does it change any of that? What if I put 172? Still crosses at -4, still crosses at 2, still bounces off 3. Right? The number in front, it doesn't change the x-intercepts or the nature of the x-intercepts. I didn't ask you. Sorry. And of course, we could make it negative. What would that do? It would like turn the graph upside down, right? But if you think about the process of flipping the graph upside down, it doesn't, like if I, Chi-Chi, what? Chi-Chi, what's that got to do with anything here? I missed something. So here is y equals to minus x cubed plus x squared minus x minus 1. If I multiply the example by -1, it flips the graph over the x-axis, right? That was one of our transformations we talked about, remember? But does that change x-intercepts? No, they stay put. It does, yeah, it does change the y-intercept, that flippity-floppity from -1 up to 1, yeah. So what I'm trying to tell you is, like, you have complete freedom to choose the coefficient in the front And you can like make that whatever you want, you know? And it's not going to change the x-intercepts. You have that freedom. But we don't have that freedom here because we have another piece of information we haven't used yet, right? The y-intercept is 10, right? So how are we going to figure out? So now the question is, what number do we need to put here to make the y-intercept 10? How do we figure that out? I'm going to argue what we should do is go back to the thing I wrote up here a little bit earlier in the class, which is that we plug in 0 to get the y-intercept, right? So p of 0 is the y-intercept. We know it's equal to what? It's equal to 10, right? But it's also equal to a times what? 4 times minus 2 times minus 3 squared. So we can figure out what a is from just dividing by that number, whatever it is. I think it's minus 72. Because that's 9 and that's 8. Well, minus 8 times 9 is minus 72, I think. So apparently, we let a equal to minus 10 over 72. And so I won't even, I mean, we could simplify that further, but I'll just leave it like that. Minus 10 over 72, x plus 4, times x minus 2, times x minus 3 squared. There you go. That is a polynomial which has those x-intercepts, that y-intercept, and will serve our purpose. This is an example of a what? A backwards problem, right? Usually, how do your problems go? Here's a polynomial. Graph it, right? But it's helpful, I think it's instructive for you to look at the problem the other way around. If you want a polynomial to have a certain characteristic feature, how do you make that polynomial? Well, we can do it with the factor theorem just like this. Let me do another example here. Suppose we want to graph y equals x to the 4th minus 5x squared plus 4. So what's our game plan? Our game plan, factor it completely and use the factor theorem essentially to guide our thinking, right? Because wherever there's a factor, there's a 0. That's what the factor theorem says. Now, I don't think we're going to need long division here for this one. This one's just the usual like quartic trig problem. You know this one? Yeah. Oh yeah. You go straight to it for me. X squared minus 4 times what? Minus 1. Good. And so we can do that. That goes x plus 2, x minus 2, x plus 1, x minus 1. So we've got x-intercepts of minus 2 plus 2, minus 1 plus 1. What's the y-intercept? The y-intercept is what? 4, right? See here, so there's 1, 2, well, all right. Yeah, the y-intercept is 4. Sorry, I'm lost in thinking. Let's see here. I don't want to. I'm not going to make the scale on the y-axis quite the same. I'm going to make this 4. So this would be like 8, right? And in fact, I don't exactly know where the local maximums and minimums are for this. I mean, I know the big picture here. What's the big picture? What did you say? Looks like a W? Okay. Yeah, that's probably about right. I mean, I was going to say big picture is that y is equal to x to the fourth plus small stuff. So like if you zoom way out, this essentially should look kind of like that. But that's not what happens, right? It crosses at -2, it crosses at -1, crosses at 1, it crosses at 2, right? So it's something like this, right? It's got to turn around to go back through -1 like that, right? It goes through this handy-dandy y-intercept of 4. I'm not sure if that's the highest it gets or if it's just getting higher past that point before it turns around. Like this is, I don't know if that's the top or if the top is over here. I mean, what I'm trying to say is this is one possible picture, but an equally valid, and I don't know if it's the case or not, it could be that it's doing like this. That's also possible. It could be that the maximum happens at 4. I just don't know. So what I draw in blue is just speculation without plugging in more numbers, you know? So when I say sketch the graph, including x-intercepts, I'm not judging you if you don't get the maximum on the right side or the wrong on the right side of the y-axis, like for example. Well, the sketch should at least have the x-intercepts right, you know. Mm-hmm. But I don't like the scale on the y. I mean, who knows what happens there? And then so that goes up, goes down here, and then up again like that. So yeah. So one of you said it looked like a W. Absolutely, I think you're spot on. Yeah. Now, why didn't I need long division for this problem? Because the factoring was like not bad, right? Well, anyway, we could do it. For an uglier problem, let's see here. How about this one? I'm going to try this one out here for size. X to the fourth minus 2x cubed x to the fourth minus 2x cubed minus 8x plus 16. Let's try to graph this by factoring it completely. And I'm going to try to use long division to aid in the factoring, all right? Now, in order to do that, we have to kind of do some creative guessing here, in the sense that I need you guys to figure out for me what is a number I could plug into the formula and give me 0. Now, statisticians will say that the chance that you're going to get this right is 0 because there's like infinitely many real numbers. So if you pick one, like the chances of picking a particular real number is 0, right? 0. 0? Well, 0 would give me 16. P of 0 is 16. P of 0 equals 16. I mean, that's the y-intercept, yeah? I heard a 2. You tried 2. P of 2 is 0, is that right? P of 2. What do we get for P of 2? So the thing that's wrong with the statistician's argument is that they're assuming that the numbers are actually given randomly, but they're not. This is a textbook problem which is based on students being able to solve it with the theorems in the section, which means that when we plug in whole numbers, one of them's going to work. Now, this is not very real world, right? Fine, admittedly, but the purpose of this is not for you to be able to solve real world polynomial problems. The purpose is for you to improve at basic math skills, and that's what this does accomplish, hopefully. Anyway, 2 to the fourth, 16. So we got a 16. Everything's 16, isn't it? This is 16, that's 16, that's 16, that's 16, plus 16, minus 16, minus 16, plus 16. We have a winner, 0. What does that mean? You're absolutely right. That is 0. 2 plugs in, gives us 0. What does that mean? That means that x minus 2 is factor. Price is wrong, Bob. No, sorry. Is he alive? Sorry. Okay, so x minus 2 is a factor. I'm going to use long division to figure out how it factors. Right? Okay, so I do x cubed, right? And that gives me x to the 4th minus 2x cubed. Hey, that's cool. So those cancel, and I'm just left with like minus 8x plus 16. Man, I bet factoring by grouping was super easy here. So how do I get a x minus 2? What do I have to multiply by x minus 2 to get that like minus 8x term? I have to do minus 8, right? Because then that gives me minus 8x. Minus 2 times minus 8 is plus 16. So again, those cancel. It gives me 0. Woohoo! All right, so what that shows you then is that, so let me just get to the point here. This tells me, I can read directly from that x to the 4th minus 2x cubed minus 8x plus 16 is equal to x minus 2 times x cubed minus 8. Do you guys know the special form trinomials? Special form trinomials. Here's a reminder. A cubed minus b cubed is a minus b times a squared plus ab plus b squared. I would encourage you to put that on your handy-dandy formula sheet because it'll help you out with a problem like this. How does x cubed minus 8 factor then? So apparently, I'm thinking a equals to x and b equals to 2. See, because 8 is 2 cubed. So that's really x cubed minus 2 cubed, right? So that's x minus 2 times, well, x squared plus 2x plus 4. That's it. How do I know that you can't factor that quadratic? It's not a perfect cube. Let's see here. Well, I know of two strategies. The one would be to complete the square and see what happens. What happens when we complete the square in that quadratic? We have x plus 1 quantity squared minus 1 plus 4, which is plus 3. So that's what completing the square gets me to on the quadratic. And so I have something squared plus a number, which means that it's prime. Can't be reduced. When you complete the square, you get a minus. That means you can you can factor it. Show of hands, who has no idea what I'm talking about right now with the completing the square and the factoring? It's okay if you don't. I wasn't taught it. I just taught it to intermediate algebra last week. It's the only reason I know at the moment to tell you this. Okay. Listen, I'm going to post a handout in course content where I explain this in gory detail for about 4 pages. I have like 10 examples that show you what I'm talking about with completing the square. But anyway, So that's it. What does that mean? What it means is that this guy right here doesn't contribute any, what? Any x-intercepts, right? So the x-intercepts are what? Just 2, right? Because look at this. Clean it up. This is really x minus 2 squared times this, x squared plus 2x plus 4 term, right? And basically this guy is never 0, right? I mean, what's the smallest that term is? 3, right? And you can see that from the formula above, right? Yeah. And that happens at minus 1. Everywhere else it's bigger. So, hey, that's everything we need to graph this thing. So what is it? It's got an x-intercept of 2. What's the y-intercept is like 16. I guess I better make that closer if I'm going to keep the same scale. I don't know. So the y-intercept is like way up here. I mean, I need to get some graph paper or something. I don't know. Yeah. And so, what's the graph look like then? So for something like this, I think it's helpful. That's 2, right? So maybe to try what happens at 1, what happens at 3. If I can see what happens at 1 and 3, then I can make my graph a little bit better, right? What happens at 1? What's p of 1 equal to? One minus 2 minus 8 plus 16. See, plugging 1 into a polynomial is super easy. You just add the coefficients. What's that? What'd you tell me? Is that 7? I mean, you might be right. 7, 8. Yeah, 7. Thank you. So that's 7. So that's about like halfway between here, somewhere in here-ish, right? And then what's p of 3 equal to? Now that's going to hurt a bit. That's 81 minus 2 times 27 minus 24. Yeah, plus 16. Help me out, guys. That would be good. Ay. 19. So at 3, it's a little bit above here, right? So my graph would be significantly improved if I could just make the x scale, like focus on, just this piece right here. But basically what's going on is it's like this. Bounces at 2, right? I can't even draw. I mean, it's the way I've drawn it, it's super tight, but basically it's just a chordic that comes down, hits the x-axis at 2, bounces there because of this, right? And goes back up. Now this one, I can tell you the global minimum for this function is what? What's the smallest the function takes, value the function takes? It's 0. It happens at 2. Right? So I can't always say something like that for these kinds of examples, all right? All right, so let's move on here. So do you guys do you have any questions about this thing I'm doing with the long division? It's kind of a sneaky step, yeah? So it's a way of factoring, essentially. Now there's a related theorem called the remainder theorem. And so the remainder theorem is kind of funny. I'll show you that here.